So in this new unit that we've just explored, we now have a new type of graph that we see. On our position versus time graph, we now have a curve, either a top opening or even a side opening parabola. Basically, they're all curves now in this unit, in this model. So the question is, how do we find the velocity? We know the slope on an x versus t graph is the velocity, so how do we find the slope of a curve? So what we're going to have to do is we're going to have to find the velocity at a couple different locations, of the slopes at multiple locations. And then we can use those multiple different locations as multiple data points that we can then plot on our velocity versus time. And the way we find the slope is at that particular point, the tangent line, because a tangent line by definition is a parallel line, or a line parallel to the curve at one point. A line parallel to the curve at only one point. So if we can draw a tangent line at the point we're interested in, then we will know that the slope of that line will be the same as the slope of the curve at that particular location. So we can know the velocity at that particular time. And we can come down to our time and match our time up and then put down whatever velocity it was that we got from the tangent line. So how do we find the velocity? We draw a tangent line at several points, whichever points we're interested in, whichever ones we choose. At that point, the slope of the tangent equals the slope of the curve by definition, because it's a line parallel to the curve at that point. And if two lines are parallel, then they have the same slope. So at that point, you know that the slope of the tangent line will have the same slope as the curve, and we know that the slope is the velocity on a position versus time graph. So the slope of the tangent line represents what we call the instantaneous velocity, or the velocity at that single particular instant in time. Whatever time we measured it at, that's the velocity at that point in time. So we call that the instantaneous velocity rather than the average velocity, what we've been finding previously. So now we have a new v versus t graph. This curve, this new v versus t curve is now going to be a diagonal line. It's no longer going to be flat lines, and it's going to show that the velocity starts possibly at 0, goes to some higher value, or it could start at some higher value and slow down and go to 0. It can now change, but it will still always now be straight lines in the v versus t graph. As time goes forward, v is increasing in this image, or in this graph, so this is definitely no longer the constant velocity model. We're now talking about a changing velocity. What does the slope of this new graph mean? Well, we can do the rise over the run, and we see that it's the change in velocity over the change in time. The change in velocity over change in time, by definition, is what we call the acceleration. It's a change in velocity per a unit time. And if we were to find that, or we can see on here that the slope of this line is constant for the entire time period. So the acceleration, which is the slope, must be constant as well. So if we were to graph that, the acceleration for this time, we would show that over the entire time, the acceleration stayed the same. So this is our new flat line. Our velocity is no longer flat. In the constant acceleration model, now we have that the acceleration is a flat line. But remember, acceleration is a change in velocity. So a constant acceleration means a constant change in velocity, or the velocity is changing at a constant rate. So the acceleration stays the same, or the rate of change of the velocity is going to be constant from now on. If velocity is measured in meters per second and time is measured in second, then the units for acceleration are going to be meters per second, which can also be abbreviated as meters per second squared. So what are the formulas that we can get from our new graphs? Well, we can get from this graph that our position is proportional to the squared of t. We could use the parabolic formulas and try and find exactly what that relationship is, but there's an easier way. If we look at the velocity versus time graph, which is the changing velocity now, we can look at the rise over the run. And as you saw on the previous board, that gives us the change in velocity over the change in time is equal to the acceleration. Acceleration is today's magic word. From our y equals mx plus b, which is our equation for the line, we can find that v is equal to at plus v initial, where A is our M is our slope, because on a velocity versus time graph, the slope is the acceleration. T is our x variable, and V initial is the starting point of our graph, and V is our final point of our graph. We can also look at the area under the curve. We know that on a V versus T graph, the area under the curve represents the displacement. So in this case, that's both a square and a triangle. So to find the total area, we'd have to add those two together. We find that our square is VI, is V initial multiplied by T. That's this change in T multiplied by the initial height, or the V initial, plus 1/2 AT squared. That is the 1/2 base times height of our triangle, but we've substituted in our V final to get that out of our equation. Instead of having V final minus V initial, we did some algebra in class, so we simplified that down to this. Then we can look at our A versus T graph, and you can see now that our A versus T graph is of course a flat line, which means that A is equal to a constant. The slope here is constant, so we know that this has to be a flat line so that A is equal to a constant number. So let's compare. What we had previously was the constant velocity model. Now we have the constant acceleration model. Previously in a constant velocity model, we had that on a position versus time graph, it was a direct linear relationship, so we could use our y equals mx plus b, and we knew that the slope of this line was a velocity. Now we have a curve. The slope of the curve still represents the velocity, but we have to use a tangent line to find the slope at independent different points. And we know that the position is related to the time squared. On a V versus T graph, in this constant velocity model, we know that we could only have flat lines because V was always a constant. This slope was never changing, so we could only ever have flat lines, and we knew that the area under the curve represented the displacement. Remember that we could go from here to here simply by finding the slope. We could not go from here back unless we had an initial starting position. You cannot just, this tells you the displacement, but it tells you how much you've changed. It doesn't tell you where you started, so you cannot recreate this graph from this unless you know your initial position. Here, now that we have a changing velocity, now our V versus T graph is going to be a diagonal, can be a positive or a negative because it can be speeding up or slowing down. Our slope on a V versus T graph is now the acceleration. Our area under the curve still represents our displacement. From this graph we can see we can get a slope, or the equation of the line. So our y equals mx plus b is the equation of the line. We can also find the area, which is our displacement. So we'd have to solve for that area like on the previous board. But we now have a new graph, and that's the acceleration versus the time. And if this slope is acceleration and the slope is constant, then our acceleration must be a flat line to show that A is constant. And of course the area under the curve has meaning here as well. That area under the curve represents the total change in velocity. So it's the area represents how much your velocity has changed, how much it has gone up or how much it has gone down. So let's look at this. As you go down, you take the slope of all the points, gives you the V versus T graph. You take the slope of the line, and that gives you the A versus T graph. You take the area under the curve, and that gives you the total change in velocity. But again, you can't recreate this graph from this unless you know the initial velocity. If you know the initial velocity was 0, and you know what the total change is, you know how far it would have to go up in however amount of time you have. Same thing from here. To go up again, you would have to find the area under the curve. And so long as you knew your initial position, this area under the curve gives you the total displacement, so you know how far you would have to go up in one amount of time. So going down, you take the slopes of the line. Going up, you take the area under the curve. That's basically it. That's how the CAM model plays out. Please remember your notebooks will be due in class tomorrow. Have a good afternoon.